Lagrangian mechanics, which will, although it's a bit difficult, it will be mind-blowing, and we highly recommend everyone to participate. It will take place after the ACT class tomorrow from 5:30 to 6. So we hope to see everyone there. And that's all for now. Yitian, you can take it away with your chemistry class. And yeah.
All right, thank you, Rich. That was really interesting. And I really encourage everybody to participate in the math competition. So, so far, well, let me share my screen real quick. All right, cool. Welcome everybody to this week's chem class. This week's topic is the periodic table, and I think it'll be one of the most fun classes that we've had. We have topics that link how the subatomic particles affect the periodic table and the arrangement, and we'll start talking about specific elements in the periodic table. So let's start with learning how to analyze every element symbol. So the element symbol, it looks like the thing on the left. The atomic number is the number of protons in that element. Every element has a distinct number of protons. And if it has a different number of protons, then it is a different element. Now, there's these things called isotopes, which have, well, the same number of protons, but a different number of neutrons in the nucleus. So it's still the same type of element, it's just a different form with a different number of neutrons in the nucleus. And so right now we're gonna go over the difference between a mass number versus an atomic mass. So the mass number is if you round the atomic mass to a whole number, and the mass number is equal to the number of protons plus the number of neutrons. The atomic mass is slightly different because, well, you can see that it's not exactly an integer number. And the reason is that, well, there are many different isotopes of an element, which means that once you give them a weighted average, they're probably not going to have a perfect looking integer number. So say you have silicon with 14 protons and 14 neutrons, that'll give you a mass of 28. But what if there is another isotope with 14 protons but 15 neutrons? Then that would give you 29. But once you average them together, also considering what percentage of all silicon in the world contains 14 neutrons versus how many contain 15, then you get this weighted average, which is the atomic mass. All right. Somebody asked, does any two atoms have the same atomic number? So as long as you have the same type of atom, so the same element, yes, you will have the same number of protons in the nucleus and thus the same atomic number. All right, next slide. So quantum numbers, which we will talk about in just a second, were derived from the Schrodinger equation. I won't talk about the Schrodinger equation today. It's super complicated. So these are the 4 quantum numbers, and you might think, oh my God, that's really complicated. But, well, there's one first thing that you should know, and it's that no 2 electrons in the same atom can have all the same 4 quantum numbers. So I guess we can use kind of an analogy of an apartment building where the principal quantum number, which has the symbol N, tells you which shell the electron lives in, and which shell is analogous to which floor of the apartment that the electron lives in. The next quantum number, which is L, the angular momentum quantum number, tells you which subshell. So in the apartment analogy, it'll be which hallway of that floor is the apartment located in. And the third quantum number, the magnetic quantum number, which is M subscript L, tells you which orbital. So basically which apartment room, which specific apartment room does the electron live in. And the spin quantum number just says that, well, there are 2 electrons that can live in an orbital, just like 2 roommates can live in an apartment. So these quantum numbers, they kind of look like a bunch of symbols, but in actuality, they kind of tell you which shell and subshells and orbitals. So like we've discussed before, orbitals have different energies, and the energy is mainly determined by which shell it's in. So as you can see outlined in the orange boxes, we have the n equals 1 shell, the n equals 2 shell, and so on and so forth. Then the second quantum number, which is L, tells you which subshell it is, and also it tells you what's the shape. So there are 4 different main shapes of an orbital, and they're just called S, P, D, and F. And so these orbital shapes kind of tell you, well, in what shaped region can the electron live? And then the magnetic quantum number tells you which exact orbital it is, because even though they can be differently shaped, the orbitals can point in different directions. So now to the fun part, where we talk about how it relates to the periodic table. So first of all, we have the S, P, D, and F blocks on the periodic table. As you can see in the left side, where it's kind of a light blue, that entire thing is the S block. And that means that the last electron that's added into the atom ended up in an S orbital. The P block is on the right side of the table, and it's in green, and it says that the last electron added into that atom was in a P orbital. And the same concept goes with the D block and the F block, which are in reddish pink and purplish pink. So right now we need to talk about the octet rule, which is a really important concept in chemistry. So that means that an atom likes to have its entire shell filled. So once we look back, so an atom likes to have all the spaces, all the available spaces in a shell filled. So a shell, remember, is like the thing that I outlined in orange, which means that an atom wants to have 2 electrons in the 1s, because each blank has a space for 2 electrons. And it likes to have 8 electrons in its outermost shell if it's in a group 2. And if there is an empty space, so like say in the apartment, there's an empty apartment complex or an empty space for an electron to go, then the apartment really wants somebody to fill it, so it reacts easily. I'm gonna check the Q&A real quick. How did this shape form? Well, that's actually a really good question. So it's based on the Schrodinger equation that I showed you earlier. And it's a lot of mathematical calculations that say, well, this electron can exist in an area or a region of this shape. All right, cool. So now we'll talk about organizing the periodic table not by blocks, but by periods and groups. So each group has the same number of valence electrons, so electrons in the outermost shell, and the number of the group is the number of valence electrons in the shell. Now also it's arranged by period, which means, well, it says which shell is the highest energy filled shell. And also very frequently elements in a group have similar properties. However, group is not the only determinant of an element's properties. So say you have like carbon and lead, although they both have 4 valence electrons, they are very different. So somebody asked, what does the 1s, 2s, 3d, 4d mean? And those are basically the names of each orbital. So in an apartment complex, you'll have like room like 501, for example. It's kind of the same thing that the 1s, 2s, and 3d, 4d, it's the same function that they do basically. They are labels for each orbital. So somebody also asked how to group lanthanides and actinides, and they're okay, lanthanides and actinides, they actually, well, even though they're at the bottom of the periodic table, that's not the most accurate way of representing it, but in the most accurate way of representing it, they're kind of stuck right between, right in the middle of the periodic table. So I'm not sure if you can see my mouse. I'll try to annotate. But like they actually belong, well, let's see if I can do it. They actually belong kind of right here. So these two groups should actually go here. But unfortunately, that would cause us to have a huge, really long periodic table, and that's just not convenient to use. Oh, this is chemistry class, and we're going to talk about periodic trends now before we get to the element. So there are some important trends that you should know that we'll talk about throughout this class. And so first we'll talk about the ionization energy, which is the energy that it takes to steal an electron out of an atom. It's to steal the outermost electron off of that atom. So when the energy increases at the top right, that means it's really hard. You have to use a lot of energy to get that electron off an atom. So electron affinity is kind of the opposite. It's how much does an atom like it when you force another electron onto the atom. So the more the atom likes it, or the easier it is, then the electron affinity increases. So electronegativity, it's actually calculated using both ionization energy and electron affinity. But what it's supposed to do is actually, it's supposed to be a measure on how well an atom steals away another atom's electrons once it's bonded with it. So a higher electronegativity element likes to steal electrons away from other atoms that it's bonded to. Atomic radius means how large the atom is. You might notice that as you go down, as you add more and more shells, the atom obviously gets fatter, it has more electrons. But at the same time, well, the fattest atoms are actually the ones on the left side of the periodic table. And that's because you're adding a new electron into a shell and nobody's really controlling that electron. It's kind of just like going woo all over the place. But as you keep on adding more, then that means that you're also increasing the number of protons in the nucleus of the atom. And so as you add more protons, then you have more force to pull them in and control them. All right, so now we're gonna start talking about the elements. So this is the really fun part. Before that, I'm gonna check the Q&A. Okay, well, first we're gonna talk about the S block, which is made of mostly reactive metals, with one exception, which is hydrogen. It's super special because it is the only non-metal in group 1. Hydrogen, you can find it as a gas with 2 hydrogen atoms bonded together, and also it can also be like the H+ that you find in acids. So it's really special, and it's also super common throughout the universe, probably the most common element in the entire universe. All right, so now we're going to talk about group 1 alkali metals. I'm going to open up the chat real quick, and you guys can tell me, where do you think you can find them? Yeah, so they are found in group 1, but let me ask another question. So where in the world or in common life can you find them? Okay, so you guys said a lot of really good answers. Somebody said potassium is found in bananas, and that's true, but not as like potassium metal, obviously. Some other people said you can find them underground, and yeah, you can find them in like salt deposits. Somebody said lithium in batteries, and that is totally correct. Lithium is a metal that's used in batteries. All right, I'm gonna close the chat. So let's first talk about the physical properties of group 1 metals. First of all, they're really soft. And they're so soft that you can even cut them with a knife, as you can see in the top left picture. And they're also not very dense. In fact, if you look at the graph that I've put on the screen, you can see that, well, for a lot of these group 1 elements, their density is below 1, which means that they actually float in water. They also have lower melting and boiling points than most other metals and worse conductivity. So why is that? Well, first of all, they are soft because they are soft and not very dense and really large because they are the largest atom in the entire period. And that's simply because, like I explained before, they have one single electron in the outer shell that's not really getting controlled as well by the nucleus. Notice that I put a sad face on the model of the atom because it says that, well, that model implies that all these electrons are orbiting like in a circle, and that's definitely not true. They exist actually in clouds. And so the other thing that I've got on the slide is that, well, there's only one freed electron for each atom in the sea of electron metallic bonding model. So what is the sea of electron models in metallic bonding? It's that, well, the electrons are free to move everywhere, and they kind of serve as a glue between the nuclei of all these atoms, which keeps them together into a giant chunk of metal. But unfortunately, since there's only one valence electron, that means that, well, it's like if you use more glue versus if you use less glue, it's probably not gonna be as effective. And that's why it's super soft, and that's why you have lower melting and boiling points, because the atoms aren't really held closely together. All right, somebody says, won't they explode? And I think that might be the next slide. Okay. The chemical properties tell you, well, why are they so reactive? And the reason is because to achieve an octet, they really want to get rid of that first electron. It's so much easier for them to just lose one and have filled shells underneath versus having to gain like 7. So that they have a really low ionization energy. It doesn't take much effort to get rid of that top electron. So in this video, we're going to show you how they react in water. The first one is lithium, which is least reactive of them all. Hopefully you guys can see the video. And remember when we talked about how lithium is not very dense, it's actually floating on top of the water. Wait, is it working? Okay. And on the left side, you can see that reaction. The second video is where an alkali metal explodes in water. And this metal is rubidium, and it's at the bottom. It's near the bottom of the periodic table. And the alkali metals get more and more reactive as you go down. And the reason is because, well, the outermost electron is further away from the nucleus, which means that it's way more out of control. So let's take a look at the video. All right, that's a pretty cool looking explosion. Rubidium exploded upon contact with water. Could you give us a link to the video? Actually, you can just search it up on your own on YouTube. That's what I did. There's no specific video that's better than others. All right. So because they are so reactive with water, that's why they have to be stored under oil. And look, lithium is so low density that it floats in the oil, which is pretty cool. All right. So these group 1 metals are often found as ions, so charged particles, and they also exist, well, these charged particles exist in salts. And so as you can see in the third picture, that's a zoomed in picture of salt crystals. And the fourth picture is the structure of what a salt crystal looks like. Notice that it's kind of like a lattice of ions. Also, once they dissolve in water, the water molecules like to stabilize the ions that get dissolved. The equation on the very left is called Coulomb's law, and it just tells you how strongly these ions are attracted to each other in the lattice based on the charges of the ions. So for example, for sodium, it's a +1 charge, and based on the distance between the two charges. All right, this is really cool. So when you drop a piece of alkali metal into liquid ammonia, which is NH3, it turns ink blue, as you can see in the picture. So that's really, really weird because you would expect that it would react like water, except it doesn't. And that's partially because, well, ammonia doesn't want to get rid of like hydrogen like water does. And also the reason that it's blue is because, well, the alkali metal does lose its electron, but now the electron is surrounded by the ammonia molecules, sort of like the way the ion is surrounded by water molecules, except in a totally different way because now the electron itself has energy levels, and when it gets excited by light, well, the blue light is not absorbed, so that's why it looks like it's blue. So I'm gonna open the chat again and tell me where you think you can find the group 2 metals. Yeah, someone said you mine them, and that's exactly correct. They definitely exist in bones and minerals, and yes, they're in the earth. That's why they're called alkaline earth metals. All right. So I'm gonna turn off the chat. Oh, somebody else said in milk of magnesia, which is absolutely correct. Milk of magnesia is magnesium hydroxide. So let's talk about the physical properties of group 2 metals first. They're harder and denser than group 1 metals. And the reason for that is, well, first of all, they're denser because their atomic radii are smaller, which means that each atom is less fat and they are condensed tightly together. They're also harder than group 1 metals because the metallic bonding is stronger. And that's because you have 2 valence electrons in the sea of electrons for each atom instead of just 1. That's also why you have higher melting points in conductivity. And this shiny piece of metal here is calcium. You wouldn't think that calcium is a shiny piece of metal because you always hear that calcium is found in milk and in bones and stuff, but in its pure elemental form, it's in metal form. And in bones and milk and stuff, you find it as the calcium ion. So after it's lost 2 electrons. So I have a quiz real quick, and I'm gonna open up the chat and you tell me what you think the answers are to the first question. All right, most people are saying less reactive. And that's right, they are less reactive. And that's because it's harder to lose 2 electrons versus losing 1. And so for the second question, as you go down the group, they get more reactive. So anybody who said that they get more reactive is correct. And that's because the electrons are further away and they're more wild and they're less controlled. Okay, so in fact, unlike all the alkali metals in group 1, which have to be stored under oil, some of the group 2 metals are safe to store in air. For example, magnesium and calcium are safe in air. Here's a picture of magnesium, and during science class, I actually got to touch and use a piece of magnesium metal. And well, we just learned that they're kind of reactive, so why don't they react in air? And that's because they have a protective coating on their surface, so that protects the rest of the metal from reacting. If you drop magnesium in water, you won't really see very much of a reaction. If you drop calcium in water, it'll bubble really, really slowly. But as you increase reactivity at the bottom of the periodic table, like we saw in the quiz questions just now, heavier group 2 elements are more reactive, and so barium has to be stored under oil or under an inert gas. And what's an inert gas? It's just a gas that does not react. So you can see a picture of barium getting stored under oil. Another interesting fact about group 2 elements is that not all of them are soluble. So in contrast to group 1 elements, we learned that their salts, group 1 salts, are pretty much almost always soluble, but that's not the case in group 2. And let me explain to you how dissolving works. So the first step that has to happen is that the solvent, so like your water, well, the water particles have to separate from each other. And that takes in energy because it takes effort for you to separate them. The second step is that you have to overcome the forces of attraction inside the ions, inside the salts, to rip them apart, and that also takes energy. And so the third step, when they combine, that's what releases energy, because now the solvent molecules, like the water, can start stabilizing the separated ions. But now here's the problem. See, if the energy released in step 3 is less than the energy taken in step 2, then that means that, well, in step 2 and step 1, then the salt's gonna think, hey, that's not even worth it, I'm just not gonna dissolve. Like, why would I do that? It takes me more energy, I have to put in more effort, and I don't really get anything out of it. But sometimes, if the amount of energy released is greater than the energy you have to put in, then the salt will dissolve. And so it's a really delicate balance between these properties. And that's why in the example at the bottom, I said that magnesium hydroxide, which is milk of magnesia, is not soluble and it forms a suspension. On the other hand, calcium hydroxide is soluble. But then you can see that calcium sulfate is insoluble. Calcium sulfate is used in plaster and stuff, while magnesium sulfate, which is Epsom salts, are soluble. So it seems really, really random. And to an extent, it kind of is, because there are so many factors that contribute to whether a salt dissolves or not. I'm going to check the Q&A real quick. What does soluble mean? Soluble means that it can dissolve in water. So if you've ever made soup, you probably put some salt in the soup, and then after a while, once you mix it, the salt is dissolved in the soup and you don't really see the salt crystals in your soup. Next slide, okay. So I asked you earlier, where can they be found? And you guys gave some really good answers. So calcium is really, really common throughout the earth. It's common as limestone and marble. And as you can see, there's a picture of a marble statue that got worn away by acid rain. And that's because limestone and marble, which are made of calcium carbonate, a compound from calcium, it reacts with the acid in the acid rain to corrode the statue. In the bottom picture, you see a cave underground that has lots of stalactites and stalagmites, and those are also made of calcium carbonate. One more interesting fact is that the sidewalk chalk that you use is actually made of calcium carbonate as well. And that chalk is made from the bones and shells of like little marine animals that lived long, long ago. And they contain calcium, and so that's why it ended up in your chalk. So somebody asked, what is acid rain? And acid rain occurs when, well, rain's falling from the sky, but then it starts reacting with pollutants in the air, and those pollutants cause the rain to become acidic. And so when you have pollution gas and it reacts with the rain, then it turns into an acid that starts falling on the statues, and it'll corrode those statues. So pollution bad. All right, next slide. This is where things get really interesting, the P block, because we have metals and nonmetals and metalloids in the P block. And so it's super diverse. And so remember how we talked about group 1 and 2 and how most of those elements have similar properties that they share with each other? That's not exactly the case in the P block. So I'm gonna open the chat and you guys tell me, what do you know about metals, nonmetals, and metalloids? Are you guys able to type? Okay, somebody said metalloids are kind of a blend between metals and nonmetals. They kind of have properties that are a cross between them. Yeah, okay, somebody said metals are solid. That's true, they're usually all solid. They're hard and conductive. Somebody said shiny, ductile, malleable. That's right. Yeah, you guys have a lot of really good answers. And somebody gave us a bunch of examples like iron, gold, silver, and copper, and aluminum. We'll actually be talking about aluminum today. So thank you for your answers. Somebody said that nonmetals can be liquid and gas. That's totally true. And metalloids are in between. They have characteristics of both metals and nonmetals. All right. Thank you guys. Those are some really good answers. So like you guys said, metals are good at conducting. Metalloids are often semiconductors, so they're kind of good, but not that good. And nonmetals are insulators, which means that they don't conduct electricity. You guys talked about malleability, which metals can bend and be flattened into sheets, or ductile, which means they can be stretched into wires and stuff. It's not really the case with the others. So first we're going to talk about group 3. Some periodic tables say group 3A, some say group 13 because, well, some of them count like the transition metals as groups. I prefer to call them group 3 or group 3A. All right, so boron is the only metalloid in group 13. And it's really special because remember how we talked about the octet rule and how usually atoms want 8 valence electrons? Well, boron is special because it's happy with 6. It's totally happy with 6, and sometimes it could hold 8. And so why is that? Well, it's because boron is so small. It's the first element that starts using its p orbitals. So it's really, really tiny. And that's why, you know what, if it has 6, well, it's full. If you look at the chemical structure of borax right there, you can see that each boron is making 3 bonds, another atom. And in each bond, there are 2 electrons, so that's 6. But when you make slime using borax, what happens is, well, the polymers in the glue, they start bonding to the borax. And they bond to specifically, well, the boron, which can make 8 bonds if it really has to. And so now you've got a tangle of glue and borax that are bonded to each other, and that's how slime forms. I know a lot of you guys love watching slime videos because my sister does. So I thought it would be really interesting to explain the science behind slime. All right. Aluminum is also in group 3, and it's the most abundant metal in Earth's crust, and it's the 3rd most abundant element at all. And so aluminum is really common, and that's why you use it for like cheap aluminum cans. So in this video, a person is using sodium hydroxide, which is lye, to dissolve an aluminum can. And so you can watch the video. So he's pouring, and then it's starting to react. And now it's, well, bye-bye can. It's kind of broken now. It's just, it's turned into a piece of sludge. At the end, it looks kind of like a piece of garbage. So somebody asked, well, why does that happen with the aluminum can when you dissolve it in lye? And the reason is that it creates a special ion called a complex ion, where oxide in the lye starts bonding to the aluminum, and it makes a charged particle called an ion that exists in solution. And so at the unbalanced equation, I was too lazy to balance it. If you look at that equation right there at the bottom, that's how it works. Fun fact about aluminum, it actually has a protective oxide, just like a lot of the group 2 metals. But the reason that it's not protected in this case is because the super strong hydroxide ion starts attacking the protective layer. And so the protective layer is destroyed and the metal gets corroded. All right. Now we get to another one of our super hot topics, which is fidget spinners. And well, I actually found a viral video on YouTube where they use gallium metal to form a fidget spinner. And why do they use gallium? Well, that's because gallium, its melting point is close to body temperature, which means that you hold it in your hand for long enough, then that metal starts to melt. And why does that happen? Well, it has a strange crystal structure that basically no other metal adopts, and that crystal structure, it starts getting unstable at body temperature so much that it's just as stable as at that temperature that it melts. So this person is using melted gallium metal that they melt in a hot water bath, and they put it in a mold to create a fidget spinner. Now we get to the even cooler part, where somebody put hand sanitizer and they set it on fire, and so the heat is enough to cause the fidget spinner to completely melt. So the metal is completely melting and the fidget spinner gets destroyed. Not popular anymore. I'm kidding. Okay, so somebody asked, could you repeat what you said about gallium being weird? Yeah, of course. So gallium has a strange crystal structure that basically no other metal really likes to have. And so that crystal structure is not as stable at the temperature that it melts. And at a certain point, the liquid form becomes more stable than that strange solid crystal form. And so that's why it likes to melt. It likes to change into the most stable form, which happens to be the liquid form at its melting point. All right. Somebody said you can put a gallium spoon in a teacup. Don't drink that tea. Drinking metal is not good for you. All right. So now we're going to talk about group 14. I'm not sure if we're going to be able to finish, but that's okay. We can continue it next time if we wish. So first of all, we're going to review what isotopes are, and then we're going to compare them to allotropes. So if you look for the definitions, both are likely to say they're different forms of the same element. And yes, that's true. But the difference between isotopes and allotropes, how they are forms of the same element. So for carbon, they have different isotopes and different allotropes. Remember how isotopes differ by the number of neutrons inside the nucleus? And that's why we have carbon 12, 13, and 14. On the other hand, carbon also has different allotropes, such as diamond, graphite, fullerenes, and soot. And they're all pure carbon. The only difference is that how the carbon atoms are arranged that causes them to become different allotropes, different forms of the same element based on how atoms are arranged. So one interesting use of carbon, the isotopes, 12 and 14, is to tell you how long a fossil is alive, or how long ago was it alive. And the reason that works is because, well, in the atmosphere, there should be a constant concentration of carbon 14. And how is carbon 14 formed in the atmosphere? Well, it's because cosmic rays from outer space cause nitrogen to turn into carbon, a nuclear reaction. So carbon 14 is constantly produced in the atmosphere. And because it's produced in the atmosphere, when something eats it, when plants use it, then it ends up in the plant. And when something eats the plant, then the carbon 14 ends up in the animal. And so living things have a constant concentration of the radioactive carbon 14. However, once the thing dies, it no longer has a source of replenishing its carbon 14. And so then the carbon 14 in its body starts to decay. And it decays via exponential decay. So how does that work? After a certain amount of time that we call, that happens that half of the carbon 14 in the sample decays. And so now you have half remaining. And then after another half-life, then half decays. So you have 1/4 of the carbon that you used to have. And so if you see the equation at the very bottom, that tells you how to calculate the age of the fossil. So somebody asked, if we use the carbon 14 dating equation to find the age of something, how do we know the initial amount of substance without knowing the age of the substance? So remember how I talked about how we know that carbon 14 gets replenished in your body because of it keeps on getting formed in the atmosphere, so it ends up in an animal's body. Well, through that, we know the concentration of carbon-14 in any living organism. And so we compare what we calculated in a living organism versus the dead one to find how long the dead one has been dead. So here's a question. And I'm gonna open up the chat, and you guys try to use the equation to calculate how long ago the early human beings were from. So if you guys have a calculator, that would be really, really helpful. Somebody asked, doesn't this get messed up by nuclear testing? Well, actually, the biggest problem with messing up carbon dating is that now the atmosphere has a disproportionate amount of carbon-12 because people are using fossil fuels so much. All right, yeah, somebody said global warming. Whoa, somebody got it right. Congratulations. I'll explain how you get the answer. All right, I'm gonna wait a couple more seconds and I'll explain the answer. Okay, this is probably one of the hardest questions that I've given you to use an equation with, but because it has so many steps, but don't worry. Okay, there we go. So first of all, we know that it's 0.7917%. So first you have to convert the decimal to a percent. So it'll end up being 0.007917. And so now we want to figure out 0.5 to the power of what is this 0.007917. And that's where you use a log function on your calculator. If you guys don't know what a log function is, that's okay, because you'll be able to learn it later on in math class, I think. And you can also ask your competitive math teacher. I think she's the next class anyway. And so now you figure out how many half-lives have passed, which is 6.98. You multiply that by the half-life of carbon-14, which is 5,730 years. And it turns out that the early human remains were from 40,000 years ago. All right. I think this will be one of the last things that we'll talk about, which is okay. Carbon allotropes. Remember how we talked about isotopes? Now we're talking about allotropes, and they differ by the way that the carbon atoms are arranged. And so in the first column, you can see diamond. And diamond is arranged where the carbons are bonded to each other in a huge network. And each carbon is bonded to 4 others. And it's a really uniform network. And the bonds are really strong. And so that's why diamond is super hard. It also has a really uniform structure, which is why the diamond surface, well, the diamond is such an organized crystal. So somebody asked, in the structure of diamond, what do the shaded triangles represent? And the shaded triangles are a way to represent bonds. And so if the bond is actually supposed to stick out towards you, then that's why they use a shaded triangle. Obviously, in a two-dimensional picture, you can't really represent a three-dimensional structure, so you have to use the shaded triangles. So graphite is the stuff that you find in pencils, and it's made of large sheets. But if you take one single sheet from the graphite, then that's called a graphene sheet. And scientists have actually been creating plenty of different structures by rolling up the graphene into a nanotube or a nanocone or a nanohorn. And it's actually one of the emerging fields of science that we have today. Fullerenes are where you have, well, about 60 carbon atoms in a soccer ball shaped structure. Okay, so I think that right now time's almost up. I'll answer one last question. What's the difference between the dark triangles and the thin line? The dark triangle bonds are supposed to stick out towards you. The thin lines are the ones that are in the plane of the paper. So unfortunately, we have to stop here, but that's okay. Next time we'll go through the rest of the periodic table. There's still many more groups that we haven't talked about yet. Right. It's about time for the next class to start. So Tina, I'll make you host and go for it.